Now, here we go. This is the lecture for Design 330. I'm in the right one, I think. Yep, there we go. It's Thursday, the 18th, and we're in our live meet. Oh, thank you. It would help if I present my screen. That's the problem. I was presenting in my other one, and I forgot to change. And did it stop flashing? Is everything okay now? Okay, so here we go. We are now we're presenting the screen too. So this is the live meet. We're going over our final detail drawings. Okay, you can. You should be able to now. Okay. Um, Also, I wanted to bring up one of the students said that the video recordings are really fuzzy and low quality. You should know that when you go into YouTube, you can set the playback quality. So these are all going in at 1080p. And depending on your internet capabilities, YouTube automatically knocks it down unless you go into your settings. In which case sometimes it gets slow with buffering. But if you're finding that the videos are a little bit blurry and fuzzy, go to your YouTube settings when you play it and click 1080p because all of the videos of these things that are being made are on fairly high. They're not lossless because that would just be too big, but they are coming out as fairly good high resolution on the input side to YouTube, and the output side is up to your system. So we've had a few people, and I just finally figured out what was going wrong for them. Okay, so a few things. We're going to finish up our final detailed drawings. Yesterday during lab, we talked about the tabulated drawings and we talked about the dimensioning standard. So I'm going to talk about those again today. And then on Monday at noon, and we also have one on March 1st at noon. We have two seminars, and these are going to be really cool. If you were in our seminars last semester where we talked about fair housing and social justice and redlining and things, we're doing the same thing this time with respect to water. Because as you know, the whole focus of this is on water. And if you don't know why you're doing something, the design is not nearly as interesting and you don't do quite as good of job with the design. So I know that we're into tons of details, and for some people, all these details are not fun, but to me, they are. I love trying to find a solution when there's literally tons of different pressures on the design going all sorts of different ways. And so this is going to be part of it. And I'm giving, because it's so important, I'm giving a credit of 4 points. If you come and you participate, not just watch the video of it, but if you're actually able to attend, you'll get 4 points that can replace any single week's submittal, which is kind of nice because if you get really busy on some week, you can just forget making your submittal that week and replace it with 4 points of this one. So that's kind of cool. It's on Monday at noon. I will give you the link for it. Professor Jeffrey Sasha is going to be doing it. His degree is in urban planning and sociology, and he actually studies this stuff. And there is a really cool site called now I'm blanking on it. I'll have to go find it, but it's just got tons and tons and tons of Social Explorer. That's what it's called. And we're trying to get access to it so that you can all have access. and it allows you to put data on top of maps. And there is an incredible amount of data. And you can actually map where water quality problems are and where they are not. And so there are some articles to pre-read. I know I've suggested to most of you that you go ahead and take one of those reading classes, and I'm not sure anybody has, but there's 5 articles to read. Now, each article should take you about 5 to 10 minutes to read and to annotate if you've done that class and know how to read and annotate. And we're working on actually incorporating that into Design 300 to teach it as part of our curriculum. How do you read articles and documents and standards and do it quickly and efficiently and pull the information out that's going to be good for you? Now, a big part of that is being well read. I spend a good half an hour to an hour every day just reading, and I pick topics that are of interest to me, and then I just start going to town with it. So these are some of the articles that I just picked up and read in their entirety. And some of these articles aren't even really articles. They're websites that just give you some more information. But pick 2 or 3 or 4 of these and pre-read. That means look at the titles, look at the first sentence of each paragraph, and annotate them to see if you can get the gist of the article, and then go just start skimming it and getting the information that kind of pulls things together. And what we're looking for is how can we tell sort of ahead of time where we might be finding water quality problems. Because we can't just go around and test everything everywhere all the time. We have to have an idea. And so by following redlining maps, it helps us get that. No. so Alex, so annotating, no. Annotating does no. And boy, I'm not a reading teacher, but when you annotate something, you write down key words that help you analyze and follow a thread. You also write down key words that you don't understand just based on the context so that you can go look those ones up. So it's really almost a keyword list and a key idea list, but you're not really summarizing a paragraph. And literally it's like bang, bang, bang. It's a speed reading concept, but it's not speed reading like I'm reading really fast. I read all the words really fast. It's more like you're taking your time and you're looking in detail, and the process, and this doesn't always work, but in the types of things that we read, it works very well in that we usually in technical documents and these explanatory documents that are presenting data, we put the key words in the first paragraph or two, and the rest are supporting statements. So you don't have to know and believe and understand all the supporting statements. You go back to those if you need to analyze it to see if it has standing. Does that sort of make some sense? So, but it's cool. It's really cool to do. At some point, maybe I'll get one of the reading professors, Leah Amberum. I don't know. I don't remember her last name. Arambell. Or one of the others to give us sort of a, hey, here's how you do this stuff. But it's a 1-unit class, and it's kind of like powerful on all this. And look, you've got some reading to do. You need to read the dimensioning standard, and you've got 3 or 4 articles to read. Now, this is a fairly light week as far as work goes, so I don't feel too bad assigning this. These tabulated drawings are pretty simple. The other drawings are pretty simple. I think you're well under the 10 to 15 hours a week that this class is supposed to take, although you can certainly take more. Okay, so that's going to be Monday at noon, and it's really, really cool. And you're going to really get some stuff. I've been working with Professor Sacha. I don't know if it's Sacha or Sasha, but it's really, really good. And for those of you who were in last semesters, he was working in an office. His wife actually works in urban planning at UC Davis. And I caught him in his wife's office last time we were talking, and he was right across from Professor Hernandez, who was one of the keynote speakers for us last semester. So if you get interested in any of this and you want like a degree and a master's degree and you can do an urban planning degree, and UC Davis is actually very, very, very strong in urban planning and environmental sciences. Super, super strong college, university. Okay, so you can read those. Let's go on to what we're sort of looking at. Here's a tabulated drawing. I'm going to go back. I'm going to go find the resources for those. They know where they are. I think they're in the what to do folder containing all this stuff. Okay, so we want to look at the nipple standard tabulated drawing. And we want to be able to make this thing. Okay, and I don't think I need to demonstrate it. I can if you want me to. But I just opened up my standard base design file for a nipple, and I made this A-size drawing from a drawing view. And it comes out with this stuff already, and it comes out with that already. So I just needed this view, and then I needed to create this view. I just needed to create the two views. Okay? And I don't care what size of this thing you use, because in a tabulated drawing, you list the sizes in a table. Okay, and here's how it works. We know that every one of these has an OD and an ID and threads on each end and a length. Where do I get those? I get those from my parameter file. My parameter file holds all those. So I can just go and look for every single one that I happen to make. I can call it up and read the parameter file and type these numbers in. Now, I like to have an actual physical model so that when I make my assemblies, it really is the right size. But I don't need a specific detailed drawing of each one. And my drawing does not need to be to scale. There's no scale on this thing. It's just sort of a picture. Okay, I do have some sort of an ID that I'm going to let you make it up. Okay, the ID just says, hey, I order this thing, and when I buy it, I'm going to call it something when I put it on the shelf in my stock area, so that if I want to use it on something, I tell one of the assemblers, go get an MB1 and hook it in. And they'll go find a box with NB1 written on it, or 1/2-inch nipple by 3 long, or something. Okay? And then they'll measure it just to make sure they grabbed the right one. And they'll look at the material to make sure that they grabbed the right one. So this is a really useful document, and there's usually a book or a computer around that people can call it up and then go get the part. That's how simple this is. So this shouldn't take you too long to make. How did I get this table? I copied one of the tables I made before and put it in here, and then I just edited it. I made revisions to the table. Sorry. I did an edit on the table. I edited the table. It's really hard to say. So you can just reproduce this, and it won't take you very long. And this is what goes in those purchase parts drawings. Okay, you got the 3 drawings that we talked about on Tuesday, the housing block, the piston, and what was my third part? Oh, and the filter. So those 3 go in the manufactured ones, and this one and your check assembly goes in the purchase parts one. Okay, the next one that I might need to look at is my check assembly, and this one's cool because it's got a minor difference. I have 2 types of check assemblies. I have one that's female inlet by male outlet, and I have another that's female inlet by female outlet. And you'll often see this on a tabulated drawing. So I called this one configuration A, and I called this one configuration B. So any of the ones that are female by male are an A, and any of the ones that are female by female are a B. So if I'm going to use a check assembly, I can say I want configuration A, quarter by quarter, 1.25 long. And I'll know to go to my shelf where I hold all these things and get something in a box called CB1. Okay? And I don't care what you call these. You can give it any ID number you want. You can call it A01. You can call it XYZ. Whatever you want. I don't care. Okay? Give it some sort of a description that tells us what it is, and then the details go over here. And so my other one is a 1/2-inch check assembly brass. It's my configuration B because it's female by female, and it's 1.62. Okay? So those are your tabulated drawings. That's it. Those go on the tabulated drawing portion. And so I have 2 of them. I would go ahead and use these 2. I'm not sure I made all of the base drawings. I think this is my female by male base drawing, and I don't think I made a female by female base drawing. But there's my base drawing for the nipple standard. Okay? Any questions on how to do that? Just some work, right? And I'm telling you guys, this is the stuff that I love. I love getting in here and just making drawings and making sure they're right and doing them well. This is where I love this stuff. And the architectural stuff is cool, but this is really where it's at. And then making it is really neat. Making it is, and you are going to get a chance, by the way. By the end of the semester, you will be able to mill this thing. You will be able to mill it. And we're going to do it all on the 2D mill, and we're just going to be able to flip it and put it into place and touch it off and move it. Like it's really going to be cool. You will be able to mill this by the time we're done. Okay, so the more we play with it, the better it'll be. Okay. Still no questions yet? All right, then my next thing I'd like to do is talk about, and this now I'm going to talk in a little bit more detail, the dimensioning standards. These are really important. You have to be somewhat familiar with these. Now, every manufacturing facility kind of has its own rules that they go by. Very few places actually follow ANSI Y 14.5. And this has been updated. I think the latest one was 2016 or 2018. They redo it every few years to make sure. But when you read the section 1.4 fundamental rules, the same. There are no changes to it. So I'm using my old one because I'm allowed to. If I use a new one, we have to pay a whole bunch of money so that you all have access to it. And we don't want to do that until there's some real changes in what we have to teach. But the fundamental rules have not changed since I started using them in about 1983. I haven't actually seen a change in here. And they'll reword it a little bit, but it means all the same thing. So this is from my 1994 copy, which is now free to use. It's okay for me to use this one now. It's no longer copyrighted. Okay, so ANSI Y 14.5 is about dimensioning and tolerancing. So here's the rules. Clearly define the engineering intent. That's it. You have to do that. Okay? You have to clearly define it. And the engineering intent is, I'm going to make a comment on it now. Form, fit, and function. That's what defines the engineering intent. Form, fit, and function. And I think you're all able to see that. If you're not able to, let me know and I'll change the sharing. I think you'll all be able to see the comments though. Okay. If not, I'll put them somewhere where you can see them. Form. What is the shape? Fit. How does it go together with other things? I need to edit that really quick. How does it fit together with other devices or the world or connections? And function ensures that it does its job. Form, fit, and function. That's engineering intent. Okay. They all have to have a tolerance. How much can the measured dimension vary from the ideal design dimension? Or how much variation can be, and here's the big, tolerated. That's why they call it a tolerance. So you'll never make a dimension exactly right on. That's not where I wanted to go. Right? I'll never get exactly 0.75. I might be off by thousandths, a half a thousandths, 1/10,000th of an inch. What's okay? I might be off by a quarter of an inch. What is okay? What can I tolerate? Every dimension has to have that. Every dimension. Okay? There are a few exceptions, and those are ones that aren't used to actually make the part. Okay? They already exist. They're not being used to make it. Or I'm just telling somebody it's about this much. Okay? And we usually indicate it in a supplementary block. Oop. And we call it our standard tolerance block. And where is that? That's this one right here, standard tolerance block. And we set it up so that the way we write a dimension, this one has 2 decimal places. I would go to the 2 decimal place line and read the 2 decimal place tolerance, plus or minus. Okay? So that's how we use these things. How we write the dimension is key to letting us know that when we inspect it, how good does the part have to be compared to what we wrote down. Okay, there's the big part right there. That's the main thing that you need to know. So I'll address Alex's question. This is how I would go about and annotate. What I'm doing here is annotating. Okay, I didn't really know maybe what that means. So I highlighted it and then I said what it means. Would I know what engineering intent means? No, so I'd highlight it and I'd say what it means. Isn't that cool? So that's how you would annotate one of these things for your use. And then to your point, I could summarize this whole thing by saying a few sentences about these. Okay. So here's another one. Full understanding of the characteristics. That means no no estimating, measuring, guessing, assuming. Okay. Oh, and what is a characteristic? Form, fit, or the function. Characteristics are whole, edge, thread, groove. Those are characteristics. The hole has a diameter and a depth. Those are two characteristics of the feature hole. So these are sort of features, actually. I should change that. Features are and characteristics are how we measure them. So this one was kind of hard to understand. So I just did a little annotation for that. And then do you need to read this stuff? No. Once you got this, you sort of got it. Sort of have it. This is all further examples, sort of like my further examples. Here's an important one. So what did I just write there? I wrote something that's spelled wrong. Okay, so no dimensions other than those necessary. Blah, blah, blah. So that's avoid double dimensioning. Only one dimension or set of dimensions to identify a given length. So where do I have that one? That one was on the best example of that one was on the filter right here. I've given this dimension, this dimension, this dimension, and I've given this dimension up here by calling out the diameter of this sphere. I've already given that dimension. I know that that dimension is 1/2 of the spherical dimension. So if I give the overall dimension, I've already given the description of how far it is from here to here. It's this one plus this one plus this one plus this one, which I've given right there. Now, the trouble with all that is somebody's got to go and add it all up. And there's likely to be a mistake made. But since I've already done it, if I want to tell somebody and add it up for them, I have to put it in parentheses. Now, it could be that I left this dimension solid and I made this one the reference. How would I decide? I would decide based on the experience of which is the most important. Okay. And so I chose this one because this is a machining function that I can program very easily versus this one, which I'd have to go and program this machining function anyway. Okay, everybody still with me on that? Okay, so the rest of these are not, here's a big one. Optimum readability. Simple and clear. Fewest views possible. If I have extra views, oh, and here's the other one. Use sections to see inside features when you need to dimension them. Okay, so those comments that I've just done, those annotations that I've made, kind of hit it as quickly and easily as possible. Okay, and the more you can practice doing this, the quicker and better you get at it. And believe me, design has tons of this in it. Standards and machining functions and things from your clients, they're all pretty important. Okay. And so you guys all know what's going on. What's the problem with water that's going on right now? Who's having the big water problems right now? Yep. And so here's a big problem is everybody knows that you leave your tap dripping a little bit so that as things freeze, the expansion doesn't break your pipes, right? Well, when you have 12 million people leaving everything dripping, you deplete your water supply. So they're going to have a terrible problem when they come back online, that they won't even have enough water because everybody was dripping their systems, which I don't blame them, right? What kind of a problem would they have if all the pipes froze and broke? Okay, and leaving it dripping does not keep you from having your pipes freeze. It keeps the freezing from being constrained. And remember that thermal expansion thing? Well, water expands when it freezes. Okay? And there's just no stopping it. The forces just keep going. And so you'll break your pipes unless your pipes can expand enough without breaking themselves. And so certain types of pipes can. Copper pipe can. Some stainless steel pipes can. A few steel pipes can, but steel pipes tend to corrode, so we don't use them. Cast iron pipes are terrible. PVC pipes are terrible. ABS pipes are terrible. So that's the problem that they've got right now, is how to bring everything back online now that it's frozen. And look, it's not really that big of a problem. It freezes all the time up north, and nobody has a real problem with it. So where does the problem lie? Anybody got a good idea on where the problem lies? Why are the pipes possibly breaking down in Texas when they don't break in Massachusetts or Maine or North Dakota? Well, I'll tell you, it has to do with something called regulations and regulatory oversight. So if you want to make sure that buildings are built and systems are designed with things like this in mind, with the future in mind, then you would apply regulations to them. What is Texas known for? Yes. Oh, amazing. Isn't that something? Texas is known for, pardon me, saying F you. F means forget you. Forget you when it comes to being regulated and following good standardized principles, especially if it might cost a company some money or cost a government some money. Okay, so now they always vote no when there's disaster relief funds. I'm sure they'll be voting yes to get disaster relief funds to repair all their cracked pipes. Just not that hard. The company I used to work for, Watts Valves, makes freeze poppers. They call them freeze poppers. They're freeze relief valves. When it gets cold, the relief valve actually opens up so there's a little place for the water to drip and the freezing to expand. It's just not hard. And many places do it. Now, would you expect for Texas to be hit like this? Right? I mean, why would you think that it could possibly freeze like this all over Texas? Well, you wouldn't unless you actually listen to scientists that have been telling us for the last 40 years, watch out, we're going to have some weirdo climate stuff happening in the next 40 to 50 years. You better start prepping for it. But, oh, there goes Texas again. FU, which means forget you. The F stands for forget. Forget you. You can't tell us what's right and regulate us and make us spend money on something that probably won't happen, and it hits my bottom line. So you'll hear me talk about this, and it's not that I'm actually very conservative when it comes to fiscal and finance and government spending and government oversight. And I happen to believe that doing a good job is less expensive than doing a crummy job. And a good job means that the people that need services get services when they want it at a reasonable price, and emergencies are never a reasonable price. So you can be thinking about that if you ever have to design something, and somebody says, well, if it breaks, we'll just throw it away, or that dumb. Always keep long-term what could happen in mind as you do it. And always sort of listen to regulations and things like these when we go over them. So there we go. That's my little bit. And we'll hear more about that on, of course, Monday in our special seminar, because guess what? There are areas in Texas that are just fine. Anybody got an idea what those areas are? They're the places that have generators in place and do have those freeze controls in place. There are a few. Fortunately, the federal rules on hospitals do apply. So the hospitals are okay from the freezing pipes. Cool. Okay. I think that's what I've got to go over. Everybody doing okay with the simulation? Does anybody need to see the simulation run again? So, Alex, you're going to be in the manufacturing world. Are you getting ready so that you can just bang those out now? Yeah. Well, that's the purpose of this thing. Is like, if I did this or I did this, it would be good, huh? So let me just show you just quickly one thing. Where did I put it? Did I put it on this one? Let me get to my simulation. So one of the things that you can think of doing, let's see, let me do my quick measurement. Let's say I need 3.875. Okay. I can set it up to do a skim cut. And if I have to take off a lot, let's say I need to do 3. Then of course what I'd want to do is hog it off with my biggest mill possible. Right? So I'm going to hog some off. And I just have to make sure that half of this 12 millimeters is less than the distance between those. And it is. going fast. So I can do what's called a hogging cut, and I can get rid of a whole bunch all at once. And we're not worried about surface finish or anything like that. So I can just go in with my biggest mill possible and take off the biggest amount possible. So that's one of the tricks that you can be thinking about, is look and see how much material you have to take off and use the biggest mill possible to do a rough cut or a hogging cut. Hogging cut isn't very nice to those poor hogs that just chomp down tons of stuff without thinking about niceties. There we go. So I'm getting close on a hogging cut. Now, if I keep my same end mill size when I'm done, I can re-zero at this point. I can re-zero it. There we go. So let me measure it. I've got to still take off 0.606. So if I'm going to move over 0.6, move up a little bit here, still cutting. Want to do that. Oop. See, even 0.6 is going to be more than half of this thing, right? And that moved my center point. Okay? But that's like moving my edge over that amount. Let me move over. A 0 there. That's pretty close. So now if I were to run it right down there, I should be okay. Because I need to take off 0.606. I'm taking off 0.601. And we'll see how I do. So that's one way that you can, and I'm sort of taking off too much because I'm taking up over half of my milling cutter. And so that would chatter like crazy. Oh, cool. There we go. Different milling cutters. That's awesome. And sometime we'll get like a fly cutter in here or a hole cutter or something like that. We'll do all sorts of things. Okay, let's just see how I got. Oh, I went just barely over. So I was shooting for that 2.9989. I'm off by like a thousandth of an inch. A little over that, but that's probably okay since I only have one decimal place here. So you see how you can sort of start thinking about the size of your cutter, doing a rough cut and zeroing it, and then using that same size cutter to move over. So you can do all sorts of stuff like that to kind of play with it as you're trying to get faster. Here's what I like to do now. Now that I've got this, I like to come here and start making circular cuts. Cool, huh? Isn't that neato? So that's how we can do some other cool stuff. Okay, that's it for class. I'm going to stop the recording.